Hi everyone. In lecture 17, we had two mini lectures. The first one was about the exponential distribution, and the second mini lecture was about multiple continuous random variables. We started that by talking about having a joint probability density function, a joint PDF, and we went through some of the properties of multiple continuous random variables, and we saw how they're similar to multiple discrete random variables, but with probability mass functions replaced by probability density functions and sums related by integrals. I then tried to go through an example, and this didn't go so great. In both lectures, the 12 o'clock and the 2 o'clock lecture, I made a typo quite early on in the example, which wasn't spotted till much later, which was a bit unfortunate. Also, in the 12 o'clock lecture, right at the very end, I simplified a fraction incorrectly, which meant the very last answer wasn't correct. In addition, in both lectures, I was running a bit short of time and went through it quite quickly. Now, the written notes online are completely correct, and I've added some more explanation of them. However, I thought you might like to see me go through it in the way I would in a lecture, but this time hopefully with no errors, and also having the luxury of being able to take a little bit more time over it. So this will be going through this example. It's example 17.3 in the online notes, or it's the final example of the lecture. And if you find this useful, you're welcome to watch this video. So as a reminder, this was our example. We have x and y being continuous random variables, and they have a joint probability density function given by this fxy, which is 4/5 1 plus xy, and this is defined for x and y both being between 0 and 1. It's 0 elsewhere. So both random variables, x and y, are going to be numbers between 0 and 1. We can also see that the intensity of probability is going to be slightly higher when x times y is big, so when x and y are both nearer to 1. And the intensity of probability is going to be slightly smaller when x times y is small, so when x and y are closer to 0. So the first thing I'd like to do here is I'd like to calculate the marginal distribution of x. Remember, to find a marginal distribution, we have to integrate out the y. In the same way as in discrete time, we would sum the probability mass function over y. We'd normally see that as summing down the columns or across the rows of a table. So here we need to integrate out y to get the marginal. So first one, marginal of x. So we need to integrate over y. So the general formula here is that the marginal distribution fx of x is the integral from y equals minus infinity to plus infinity of the joint distribution fxy dy. So that's what we need to do here. So for us, we've already said that x and y can only take values between 0 and 1. So below 0 and above 1, this integral is going to be 0, and we don't need to worry about it. So for our example, it's sufficient to look at the integral going from y equals 0 to 1, because those are the only values that y can get. We then substitute in our value for fxy, that's 4/5 1 plus xy, and to integrate that with respect to y. So we just need to do the integral with respect to y. So as far as this is concerned, x is just a constant that can be treated like any other constant. So I'm going to do this by taking my 4/5 outside. Then when I integrate 1 with respect to y, that gives me y. When I integrate xy with respect to y, the x is just a constant, so that stays out the front. And the y becomes a half y squared. So this will be half x, the constant x, y squared being the integral of y. And that goes between y equals 0 and 1. So if we evaluate that expression at y equals 1, then y is 1. A half x y squared, that's a half times x times 1 squared, which is a half x. Then if we evaluate it at 0, y is 0. That half x times y squared, y is 0, so y squared is 0, so that's all 0. So we get 4/5 1 plus a half x, and that is, of course, for x between 0 and 1. You can't see that because my face is in the way, for x between 0 and 1. So that has found the marginal distribution of x, which we have found by integrating over y. Similarly, we could find the marginal distribution of y by integrating over x. The second thing I said we wanted to calculate was a conditional probability density function. So let's do the conditional of y given x equals a quarter. I think in one of the lectures I did this for x equals a quarter, and one I did x equals a half. Doesn't matter, the principle is the same, but the answer for x equals half turns out to be a little bit boring. So I'll do this for x equals a quarter here. So we said how we form a conditional PDF by taking the joint PDF divided by the marginal. And that's exactly the same as we did with discrete distributions, where the conditional PMF was the joint PMF divided by the marginal. We often talked about that in terms of dividing a row or column of the table by its row sum or its column sum, or equivalently by taking the row or column of the table and normalizing it to 1. It's not, here it's not, you can't really interpret it that way. You just have to sort of write down the fraction. So the general result here is that f y given x is fxy of xy, the joint, divided by fx of x, the marginal. So here we specifically want fyx of y given x is a quarter. So that's going to be fxy of 1/4 y divided by fx of 1/4, because we're conditioning on little x being a quarter here. So let's look at the top and the bottom of that fraction here. So fxy of 1/4 y, well, for that we just have to read our joint probability density function from up here, 4/5 1 plus xy, and we have to put in x equals a quarter. So that will be 4/5 of 1 plus a quarter y, because that's 1 plus xy, but with x equals a quarter. So that's the top of the fraction. The bottom of the fraction is fx of 1/4. So to find that, we go up to our previous bit of the example where we found the marginal distribution of x. We found it was 4/5 1 plus a half x. So the marginal distribution of a quarter is 4/5 1 plus a half x is a quarter. And so half times a quarter is an 1/8. So that thing in there is 9/8. I'm actually going to leave the 4/5 outside. So I'm going to write that as 4/5 times 9/8, because I can see I'm going to get a nice bit of cancellation in a minute. And so the joint distribution of y given x equals a quarter is the fraction of those two things. So f y given x equals a quarter is the thing on the top, 4/5 1 plus a quarter y, divided by the thing on the bottom, 4/5 times 9/8. And you can see that the 4/5 is going to cancel now in a pleasant way. So that's going to leave me with 8/9 1 plus a quarter y. And again, that's for y between 0 and 1, because we know it's impossible everywhere else. So there we found the conditional distribution by taking the joint and dividing it by the marginal. The third thing I suggested we could do is we could find the covariance between x and y. So covariance. So it's normally easiest to calculate covariance using the computational formula. So remember that the computational formula is that this is the expected value of xy minus mu x mu y. That's the covariance of x and y. So we need to find the expected value of xy, we need to find mu x, the expected value of x, and mu y, the expected value of y. So I'm going to start by finding mu x, the expected value of x. So we can find that using the marginal distribution of x we had earlier, because we know that this is generically, it's the integral from minus infinity to infinity of the marginal distribution of x with respect to x times an x in there. So that's a general formula for the expectation. Here, again, x can only be a number between 0 and 1 for us, so we can make this an integral between 0 and 1. And we have x, then we have to look at the marginal distribution of x. That was the first thing we did in the example. It's 4/5, 1 plus a half x. So we can put in here 4/5, 1 plus a half x, because that's what we calculated as the marginal dx. And so now we have to go ahead and do that integration again. I'm going to take the 4/5 outside, and multiplying the x into those brackets, I'll get x plus a half x squared. So doing the integral, the x becomes a half x squared. The half x squared becomes 1/6 x cubed, because we have to divide through by 3. So 1/6 x cubed, evaluated between x equals 0 and 1. And so if we do that evaluation, we get a half plus a 6 minus 0 minus 0. Because when x is 1, we have a half plus a 6. And when x is 0, both of those terms are 0. And that all comes out as 8/15, because a half plus a 6 is 2/3. So that gives us 4 times 2 equals 8 on the top, and 3 times 5 equals 15 on the bottom. So we get 8/15 as the expected value of x. We also need the expected value of y, or mu y. Now, there's two ways we can calculate this. One is that we can go through the similar exercise we did before. So we first find the marginal distribution for y by integrating out the x. Then once we find that marginal, we do the integral of y f of y dy in the same way as we've just done the integral of x f of x dx to find the expectation of y. And if you want to do that yourself as an exercise, I would encourage that. However, in this case, we can also see that if we look at the original PDF up here, that is symmetric under x and y. Like if we swap the roles of x and y, we'd still have 4/5 1 plus xy. I guess it would be 4/5 1 plus yx. So there is a shortcut here, which we say that, well, the marginal for x and the marginal for y must be the same thing, because it's all symmetric in swapping y and x, and thus the expected value must be the same. So if you understood what I've said there about symmetry between x and y, you can see that this must also be 8/15 for the same reason. On the other hand, if you didn't follow what I just said about symmetry, then it's perfectly okay for you to go through the exercise of finding the marginal for y by integrating out x and then calculating the expectation. It might be a good exercise even if you do understand the symmetry argument. But to try and keep this video an at least moderate length, I'm just going to say we know it's 8/15 either by symmetry or by you doing the exercise. So to finish off the formula for the covariance, we also need the expected value of xy, which is a little bit trickier. So we also need the expected value of xy. So we know by the law of the unconscious statistician that the way to find that is we need to integrate from, I'm going to put the integral over x on the outside, I think. X from minus infinity to plus infinity, integral from y from minus infinity to plus infinity, and then we have little xy in there, fxy, xy, dy, dx. So to find the expectation of a function of x and y, such as x times y, we have to put that function inside the integral. Here it's little x times little y. And then we integrate that against the joint probability density function, and we have to integrate that over y and x. This is the same way as when we were doing this with discrete random variables. We had a sum over x and y of the function of x and y here, little x times little y, times the probability mass function. So by the law of the unconscious statistician, that's the formula for the expected value of x and y. So in our case here, again, we know that this is 0 apart from when x and y are both between 0 and 1 for our example. So for our example, this can be integrals from 0 to 1. And xy is xy, and the joint probability density function we've said is 4/5 1 plus xy. That's the thing that we were given at the top there, highlighted in yellow. Dy dx. I'm going to do a bit of rearranging, which is I'm going to take my 4/5 outside. And I'm going to multiply my xy into the bracket. So that's going to give me xy plus x squared, y squared. So now we've got this double integral. We've got an integral over y and an integral over x. So you just have to do those one at a time. Here I'm going to do the integration over y first, and I'll come back to the integration over x later. So I'm going to perform this integration over y. So I'm still going to have this 4/5 outside and this integration over x. But now I'm going to integrate this over y. So again, I'm treating x as a constant, and I'm integrating the y bit. So x times y, x is just a constant, y becomes a half y squared. That's half xy squared. Similarly here, x squared is just a constant, but y squared becomes a third y cubed. That's a third x squared, the constant, y cubed, the thing I've integrated, and that's going from y equals 0 to 1. And I still leave my integration over x around the outside. I'll deal with that in a minute. So I now have to evaluate that at y equals 1 and y equals 0. So I still have this integration over the x outside. So the first term at y equals 1, that would just be a half times x times 1 squared, which would be a half x. The next term will be a third times x squared times 1 cubed. That's a third x squared. And at y equals 0, both those terms will be 0, because that'll be 0 times something. And just to neaten that up a bit, that will just be a half x plus a third x squared. So now I've done all the integrating over y. I've still got my integration over x to go, so I'm going to do that now. I've still got 4/5. Half x squared, half x becomes a half times a half x squared, so that's a quarter x squared when I integrate it. A third x squared will become a third times a third x cubed, so that will be 1/9 x cubed. And I have to evaluate that between x equals 0 and 1. At x equals 1, that's a quarter plus 1/9, and at x equals 0, that's 0 and 0, giving me 4/5 times a quarter plus 1/9. That comes to 13/45. So that's the expected value of xy. Quite a lot of steps there, but it is just integration, remembering that when we did the integral over y, we had to treat x as a constant. So finally, we can say that the covariance of xy is the expected value of xy minus mu x mu y. The expected value of xy we've just calculated there. It's 13/45. Mu x and mu y, we calculated those up here. Those were both 8/15. In general, they're not the same, but in this particular case, they are. That's minus 8/15 times 8/15. And you can, if you put that all over a common factor and work it out, you get 1 over 255, which is 0.0044 approximately. So here we get a very small positive covariance. That also means the correlation will be positive. So X and Y, they slightly agree with each other, as in when one of them's big, it's slightly more likely that the other one will be big, because they have a slightly positive covariance. On the other hand, the covariance is near 0, so that's sort of almost independent, but not quite. So that was me going through, again, the example on multiple continuous random variables. That's example 17.3 in the notes, and I hope some of you perhaps found this useful.